So now a quick brief review of dynamic failure. What we end up with on last Thursday is we know tensile strength is the quantity we care the most when you have a static loading, right? We say when the stress is limited to a certain value, and if your stress applied to the material is higher than the tensile strength, then failure is going to happen. That's what this thing here means, right? Now, for dynamic failure, we have another quantity we introduced called the K1C, right? It's called a stress intensity factor. And here is the equation to quantify how you calculate K1C, all right? Now, what K1C does is imagine if you have a material, something like that, then you have artificially created crack on the surface or somewhere on the internal of the material. You are going to apply stress in a global fashion. Apply stress here, 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 here. Okay, now if the length of this crack is 2a, length of crack equals to 2 times a, then your stress intensity factor, this K1C, basically tells you what's the stress going to be at the crack tip, all right? Because we all know when you apply stress to a material that has a crack, the stress here is going to be very high because of a stress concentration, right? Because all here, this is all cracked. Therefore, when you apply stress, the stress at the tip will be really high, right? So we all had a experience of buying, for example, a bag of candy, right? Usually on a plastic bag, a bag of candy, you see something like those. Candies. I don't know how to draw candies. Something like that. Or chocolates, right? And then here you have the ceiling or whatever. If you want to tear it open, if you want to open the candy, you always start with this notch, right? You try to tear it apart, right? So similar things here. When you have a pre-existing crack, the stress intensity factor is designed to take into consideration of the stress concentration, right? Now that tells you the stress at the tip equals to the global stress, which is stress applied globally, all right, equal to F divided by A, right? Times square root pi times A. A is half of the crack length, right? Okay, now stress intensity factor K1C is a material property. You can find this K1C value on any of the engineering design handbook, all right? Okay, so once we know that, then we can do lots of analysis, which hopefully we have time to cover it. If not, that's fine too, because this is probably a graduate level class content. Okay, so what we're going to do next is we know this dynamic failure, right? So we design a material system. How are you going to take into consideration of dynamic loadings, all right? There are lots of parameters out there you need to consider. So let's start with the concept endurance limit. All right. The concept of endurance limit means it is for prototype design. It is a quick estimation of dynamic strength. All right, so basically the endurance limit is a quick estimation of dynamic strength, all right? Similar concept to static strength. Okay, so for most of the structural materials, either aluminum alloys or stainless steel or titanium alloys you guys like to use, most of the time this endurance limit, SE prime, is roughly equal to 0.4 or 0.6 times ultimate tensile strength, right? So in other words, it's equal to about 40% to 60% of the tensile strength on a static loading condition, right? So this SE prime, it's called endurance limit. And this SUT, we all know this is called ultimate tensile strength, right? This is a static loading condition point of view. So this is a number you guys can find from McMaster or from other websites, right? It tells you what's some static loading condition, what's a on a static loading condition, what's the maximum stress you can apply, right? That tells you when we have dynamic loading for most of the engineering materials, the strength, the dynamic, this is dynamic strength. Dynamic strength is equal to roughly 40% or 60% of the static strength, right? Okay, now one thing we always know is most of the time shaft is made out of steel, right? Because steel, it has high tensile strength, and also steel, it has, relatively speaking, good hardness, right? Better than all the alloys out there. So for steel, the endurance limit SE prime, it's equal to 0.5%, sorry, 50% of ultimate tensile strength, or 100 KSI, 700 megapascal. This is when you have SUT smaller than 200 KSI or 1400 megapascal, depends on whether you use English unit or metric. All right, so the condition over here is if you have static tensile strength less than 200 KSI, or in other words 1400 megapascal, then your dynamic limit, which is we call endurance limit, equal to 50% of the static strength, all right? Or otherwise, if it's higher than that, then we just take 100 or 700 megapascal, depends on what unit you're using, all right? Okay, so this gives us a quick estimation of your dynamic loading strength, or in other words, dynamic loading limitation, right? Okay, so this is a new concept, SE, and we will be using this to guide our designs of shaft or other component we're going to do in the rest of the class, all right? Okay, so see here. So we're doing dynamic loading. Dynamic loading, in other words, it's going to cause fatigue. In other words, fatigue is dynamic failure. In another form, right? You can say fatigue is ultimately when your dynamic loading reaches the limit, the material, especially metal, fatigue will happen, right? So fatigue failure analysis is important. It's very similar to what we did before when we had a maximum shear stress or distortional energy method, right? Okay, so here we have some method out there we can use. The first one is fatigue life method. First one is stress life. That assumes it is a stress caused the failure in dynamic motion fashion, right? So we need to look into the stress. Second one is strain life method. So this method it assumes it is a strain caused the ultimate dynamic failure, right? So we need to focus on strain. And the last one called linear elastic fracture mechanics method. All right. Or we also have another method out there which is called fatigue strength. And endurance limit. All right, so the most popular one, which we'll be spending quite a lot of time, is called strength and life, which is SN diagram. Well, there's a new term we have been talking is life, right? Strength we'll know, strain we'll know, what's stress we'll know that, right? But what is life? Life means how many times of dynamic loading you can carry before it fails. So that's why it's N. Now take an example of bending a copper wire, right? Typically you have to bend it a couple of times before you break it, maybe 10 times or 12 times. That number is life. Tells you how many times of dynamic loading it can carry before failure happens, all right? Okay, so that is what we care the most, because for dynamic loading, we know the endurance limit can be estimated by this, right? But how many times of loading it can carry, that matters, because that we can have an estimation of how many hours of life it has, right? Or how many cycles it can carry before failure happens, right? Okay, so let's see next. So endurance limit is a very powerful estimation of dynamic failure. So in reality point of view, there's lots of influence factors will also influence your endurance limit. So let's take a look at what kind of modification factors are out there we need to consider when we have endurance limit. So endurance limit modification factor. All right, so first one, surface conditions. Okay, so give you a quick example. Yeah, I have two rods. One of them has been polished really nice, all right, very smooth on the surface. Well, the other one is rough on the surface, so right out of forging process or whatever. They have the same diameter, the same length, and the stress applied on the same magnitude, right? So if I say this has a tensile strength of sigma TS prime, this one has a tensile strength of sigma S double prime. Take a guess, which one will be higher? Prime or double prime? How many of you say prime? Will be higher? How many of you say double prime will be higher? Right. Yep. All right. You guys are smart. I know that, right? Of course, it'll be the smooth one will be higher, right? Because if you look very closely at those rough surface, you are going to create a lot of small surface crack, which will induce a lot of surface stress concentration, right? So see here, this is an exaggeration of a realistic case, right? I have a crack on the surface. Usually, whenever you have any mechanical system, you don't have a crack, right? But crack, in other words, if you have a rough surface, for example, like that, if you zoom in at this location, you are going to see these kind of things, right? We have these kind of things, we know the stress at the crack tip is higher. So in other words, if you have a rough surface, you have lots of high local stresses, which of course is going to give you less strength. Make sense? All right. That's why whenever you have a mechanical system, you're trying to do a very good job in polishing, make sure that it's smooth. There's no surface. There's a good surface roughness, right? The roughness number is low, in other words. Okay, so surface condition matters, all right, for shaft or for any of the component under dynamic loading, right? Especially we know if you have local stress concentration on the dynamic loading, it's going to exaggerate it because we know dynamic loading has less strength compared to static, right? Okay, so surface condition matters. Second, size in terms of geometry. Now, couple extreme cases. If I have a steel rod, what's wrong, Andres?
Is that sigma, is that strength or stress?
Strength.
Strength? Oh,
Yeah.
okay.
Tensile strength. TS. Tensile strength.
Oh, okay.
Okay. All right. So if I have a steel, and here I have a diameter equal to, for example, very common, 10 millimeter. Right. And again, apply loading on it. Apply stress. Right. Or I have a very, very small steel wire. Let's have some exaggeration. This diameter equals to 10 nanometers, right? Now, again, I am going to consider the tensile strength of these two materials. They have the same surface finish, same material. The only difference is diameter. So take a guess which one is higher, prime or double prime? How many of you say prime? How many of you say double prime? All right, those people say double prime should get some extra credit, huh? It's this. Yes? Oh, okay. All right. Why is that? Okay, first of all, let's say you guys heard of this term? Nanotechnology?
Can you hold it up a little bit more?
Sure. You guys heard of something called nanotechnology?
Yeah.
Right? So why nanotechnology is so popular or draws so much attention?
Small.
Because they're small? So we like small things? I don't think it's true for everyone. Some people like big things. Texas, right? We all like big things. Everything's big in Texas. Nanotechnology is because when material, the size goes down to less than 100 nanometers, the mechanical, electrical, or magnetic property gets significantly increased. So, for example, an example of carbon. So you guys have heard of carbon nanotube, right? So a lot of you heard of it, right? Why carbon nanotube is so popular? It's just carbon. It's because carbon nanotube, the Young's modulus is about 3 times higher than steel. It is just carbon, but it's 3 times stronger than steel. That's incredible, right? One of the explanation, a quick explanation of why the size goes down to nano is better is because when you have a big size material, you have a higher chance of having internal defects, right? When you have nanoscale, because it's so small and all the crystals so well aligned, you have less internal defects. Now remember last Thursday when I'm about to finish my teaching, I said for most of dynamic failure or even static failure, it happens in between 2 grand boundary conditions, right? Because all the metals, they are not like uniformly atoms next to each other. They have grands. So failure always happens in between the grand boundary conditions. So you have more chance of having defects and grand boundary conditions here. But here, since it's so small in nano, you don't have those things. So you have less chance of defects. Also, you have less grand boundary conditions. Of course, it's going to be better. Make sense? All right. So that's why nanotechnology is so important and so draws so much attention, right? Okay. So size, we also know it'll influence. It's a modification factor, right? So probably now you can guess if the size is big, probably your endurance limit will be what? Lower, right? If the diameter or if the size is small, probably your endurance limit can be a little higher. Okay. All right. So just going to have a qualitative analysis. We'll go to quantitative analysis later on, right? The next one is loading. It's so easy to understand, right? So if your loading magnitude is high, of course your endurance limit will be lower, right? So that's nothing I need to say. Temperature, of course, temperature is important because most of the structural material we use are metals, right? So for metal, here's something interesting. Your tensile strength is a function of temperature. So when the temperature is higher, your tensile strength goes lower. That's easy to understand, right? Have you guys seen how they make those? Last night I just watched a video. How there's one program called How It's Made. You guys don't like it, right? So the way they, you don't like it. Okay. All right. How it's made. There's one video about how they make ranch. Is this how you spell ranch? Definitely. No T? Anyway, how they make ranch is first of all they cut a steel rod and then they heat it up to really high temperature, about 1800 Fahrenheit, to become red hot, and then they can do forging. Why they have to heat it up? Yeah, because your strength, once it's at a high temperature, it's lower, right? At room temperature, still is so hot, you cannot deform it very easily. But once it's at a high temperature, use the same amount of force, same amount of stress, you can deform it. You can cause plastic deformation. You need to understand, right? Yes? Okay. Another inappropriate example is probably I told you guys already. Everybody we chew chewing gums sometimes, right? So initially when you take it out of the package, it's very hot, right? When you chew it for a long time, it becomes soft. And then when you go to a drinking fountain, try to drink some really cold water, what happens? It becomes hotter, right? So at a lower temperature, your strength or your modulus is higher. At a higher temperature, it's lower. Easy, right? So therefore, when you consider endurance limit, temperature matters. At a higher temperature, it's going to be lower for sure, right? Okay, so the last one is reliability. I don't know why. What's wrong? It always showed 9:40 a.m. here. It's weird. Because I was teaching a morning class of graduate level class. I'm like, why it's always 9:41? Why time doesn't go? Anyway, yeah. Okay. So you guys let me know when it's 4 o'clock, all right? So reliability, right? How reliable your system want to be? You want to be 99.99%, or you just want to be 50%? Depends on how critical your component is, right? So that also matters. All right. So let's see here. Now we'll come to quantitative analysis later on, all right? So first of all, we're talking about dynamic failure. first method we mentioned is stress life. All right. In other words, it's S and S is your stress, N is number of cycles of loading. All right. Okay, so they did this testing, and the plot looks like this. I'm going to summarize this method just in one plot. Okay, so the x-axis here is number of stress cycles. Now the stress can go like this. Stress as a function of time can be positive, negative. So this is called one cycle. From here to here, right? When it finish one period, that's called one cycle. This is number of stress cycles, which we use N. And over here, I have fatigue strength. Fatigue strength. Okay, so of course the number of cycles is going to be a high number. Well, let's say we start with 1. I 10 to the 0, 10 to the power of 0, and we have 10 to the 1, 10 to the 2, 3, 4, 5, 6, and 7, and 8. Let's just stop here, right? All right, so number of cycles start from 1 all the way to 100 million, right? Okay, so y-axis is my fatigue strength. Fatigue strength means how many under this number of cycles, what's the strength of the load you can apply, right? Okay, so it goes like this. Into 3 and significantly drop, then becomes flat. All right, so there's 3 stages over here. First one, 10 to the 3 roughly. Second one, roughly 10 to the 6, and beyond. Okay. All right. So in mechanical design, if it's less than 1,000 times of a cycle, we call it low cycle. And over here, we call it high cycle. Past 10 to the 6, we call it infinity. Right? So this is how we define number of cycles. Okay. Now, who can tell me what is this number here? Right here. What is this number should equal to? And compared to static, yeah, that is just equal to static tensile strength, right? Just one cycle, which is just exactly as tensile strength, SUT. All right. And another interesting point is you see after past 10 to the 6, it's going to reach a plateau, right? It's going to be steady, right? It does not significantly decrease anymore. So here, this number, we give a name. The name is called endurance limit. That's something we already learned, right? Makes sense, right? What does endurance limit mean? If your stress is lower than that limitation, no failure is going to happen. Makes sense, right? Okay. So here, SE, which is this lowest number, which becomes stable after 10 to the 6 number of cycles, 1 million cycles. Endurance limit. Okay. All right, and just a quick reminder, most of the time it's for ferrous metal and alloys. So any metal contains iron, all right? So it has this fatigue endurance limit. It's very obvious, okay? And some other metal, for example, glass or ceramic, those things, they don't really have they don't have a very obvious endurance limit. It does have, but it's not as obvious as in a steel or an iron-based material, right? And again, iron or steel are the fundamental materials we use for lots of rotating parts, right? Okay, you know, most of the bearings they're made of irons, right, or steels, right, stainless steels. Okay, all right. So just like stop there. I don't have to say anything about these. Just skip this. Okay. All right. Next important thing is endurance limit. Modification factors. Okay, so we know endurance limit is important by looking at this table, this plot over here, right? That tells you what's the stress you can apply, dynamic stress you can apply before before you fail it, right? So if you want to have a shaft, for example, the shaft in your car, right? It's going to, so to speaking, have infinity long life, right? You don't want your axis to broken or something, right? So you have to consider the endurance limit. But like I mentioned, the lots of parameters will influence it, right? Load, temperature, reliability, or size, or surface conditions. So next, we're going to see how we can quantify those influence parameters, okay? All right. Okay, so the fundamental equation is very easy. It's easy, right? Doesn't have that many parameters. Well, there's only 6 parameters you need to consider, right? Well, let's not worry about those things. We'll go through them one by one. We know this. This is how we define in the beginning of the class, right? This is the endurance limit, SE prime. That's what you find. Can I move up? Okay, so just K, KB, KC all the way to KF, right? SE prime. Okay, so remember SE prime? See here? We can have a quick estimation of SE prime by using this equation inside this box, right? SE prime equals to half of the SUT or equal to 100 or 700, depends on your static tensile strength. Okay, so SE prime you can quickly estimate. Then, by considering all these modification factors, you can get a modified, or in other words, more realistic endurance limits. Make sense? All right. So next, we're going to look into these 6 parameters one by one. Okay. And let me see. Okay, the first one is Ka. It's called surface condition modification factor. All right. Kb is the size modification factor. And this Kc is load modification factor. All right. And there are 3 more. KD is temperature. And KE is reliability. Okay, and the last one, yeah, miscellaneous effects. Okay, and of course, this SE prime is nominal endurance limit.
Nominal or?
Hmm?
Normal?
Nominal?
Yeah, nominal without the R, right?
Oh, okay, sorry. Or in other words, you can just say call it theoretical endurance limit, right? The last one, SE, is modified endurance limit. Okay, so 6 parameters. The whole purpose of using these 6 parameters is we're trying to see on a realistic point of view, if you have different size, different temperature, or different loading conditions, or different reliability issues you want to consider, how the endurance limit is going to be changed, right? Okay, so next 10 minutes or so, I am going to, hopefully we can have time to cover 2 of the parameters. So let's look into Ka first. For Ka is the equation you can use, equal to A times SUTB, all right, the power of B. SUT is tensile strength, and A and B are parameters or coefficients. Now again, Ka is surface condition, right? So we have different surface finish. You're going to have different A and B. You can imagine that, right? Okay, so if you have surface finish, first column, for most of the time, for those rotational parts, is 4 different kinds of a surface finish. First one, you can have it grounded, so let's just call it ground. Or you can have a machined, all right? Just use the lathe to machine it. Or hot rolled, lastly, as forged. Okay. All right. So for these,
what was the first one?
ground, or you call it grounded. Factor A, factor B. Okay. Here you have SUT in English unit KSI, or your SUT is given in metric. Same thing here. If your tensile strength is given in English units, or if your tensile strength is given out in metric, and they are different. So these are the values. Now, as you can see, those numbers are their own. Not, it's not so weird. It's because everything is based on experiment, right? So empirical. So therefore, it's based on a bunch of testing. So that's why these two parameters come to play. In other words, all the testing data are curve fitted, and the parameters are generated by a computer. All right. Alright, so for parameter B, actually they're the same, no matter which unit you use. To just be consistent, I'm going to write in one more time. Okay. This table basically gives you the parameter of A and B, and how based on the surface finish, based on the final machining method you use, and then you can just pick the parameters, right? All right, so let's take a quick look of these KA. Huh?
Why are these numbers the same? Just
because the power of B, they are the same. It's because this is based on the experiment. So when they did the curve fitting, no matter which, whether you use English unit or metric, they are the same to the power, right? But the coefficient multiplied in front are different. Okay. All right. So let's look at a quick example. The first deal has a minimum automatic strength of 520 megapascal, and a machined surface estimate the KA. All right, so now key conditions here. First of all, it has minimum strength of 520. That's SUT 520, right? And it has a machined surface, so probably I need to choose this. Then it's giving out in metric, so this number is what I need to use, and along with this, right? So just pick these two numbers, plug into that equation, should give you the Ka, right? So let's take a look at what is Ka equal to in this case. So Ka equal to A SUT to the power of B. From the table, your A is 4.51. SUT is 520. Oh, in the future, if this unit is not megapascal, you have to transfer into megapascal, right? Because see here, everything is given out in megapascal, right? Okay, 520 megapascal, and B is negative 0.265. All right, multiply that together equal to 0.86. Okay, so most of the time, when you calculate out your Ka, it'll be less than 1, right? Why is that? SE equal to all your Ka, Kb, all the way to Kf times SE prime. This is my theoretical endurance limit, but depends on your conditions, modification factors. It's going to give you a more realistic value, right? At a high temperature, of course, it's going to be lower. At a big diameter, of course, it's going to be lower. So all these parameters, most of the time, they are smaller than 1, right? So in some equations, if we hide them, which I'll tell you later on, but most of the time, 90% of the time, it's less than 1, all right? If your calculated number is like 125, probably it's not right, okay? All right. Size factor. All right, size factor. It's considered as 2 different components here. First one, if your beam is on the bending and torsion, then the Kb equals to divided by 0.3, negative 0.107 equal to roughly 0.879, and d to the negative 0.107, or equal to 0.91, d negative 0.107, or equal to 1.24, d negative the power of 0.07, or lastly 1.51, d negative 0.57. All right, so of course you have 4 different conditions. That is all decided by the diameter of the shaft of the beam. 51, 254 millimeters is for this case, and over here is 2.79 to 51. Millimeters, or if you use inch, here is 2 inch to 10 inch, and the first one is 0.11 to 2 inch. All right, sorry, I have limited space. Use the red over here, so therefore you don't get confused. All right, so the first one is 0.11 to 2 inches, right? The second one is 2 inches to 10, and the third and fourth, they are just in a metric, they're the same, right? If you multiply by 2.45, right? Okay, so depends on your shaft diameter, you have different modification factors for size when the beam is on the bending and torsion, right? Now, if you have axial loading, in other words, tension or compression, right? This Kb is just equal to 1 at this condition, right? Now, in order to consider that, Kc will kick in and then take care of the axial loading conditions, right? Okay, so let's see here. Now, sometimes you might ask me, what if my beam is not a circular shape, right? What if it is a rectangular for most of the for most of the simple beam problems we have been doing, right? They're all rectangular. So if you have rectangular, how is that going to be? So we have something called equivalent diameter. All right, after this concept, I'm done, right? One last thing. So DE. So DE equal to 0.7 times D, or equal to 0.808 H times B square root. Remember, most of the time we have rectangular base times height, right? That is your addition here. If your load is applied like that, base times height. B is base, H is height, right? Now, this is for hollow rod.